Even now, a formidable pressure system is gathering over the Rocky Mountains, a silent giant stirring to life. With a core pressure of 986 millibars, it possesses an intensity more characteristic of deep winter than the gentle unfolding of late April. This is not an isolated event. It marks the beginning of a 12-day atmospheric sequence now firmly established over the North American continent. A relentless stream of energy from the Pacific is set to traverse the Rockies every 2 days, a rhythm that promises to unleash immense power over the Central Plains. The potential consequences are vast and varied, a catalogue of nature's force: tornadoes, blizzards, wildfires, and floods, all accompanied by winds reaching 60 miles per hour. While forecast models concur on this overarching pattern, they diverge on its ultimate expression, raising a critical question. Will this energy consolidate into a single, memorable catastrophe, or will it fragment into a series of smaller, less remarkable storms? The atmosphere is about to reveal its intentions, and we invite you to follow this unfolding narrative here on Calm Space. We are also interested in your perspective from wherever you are watching. When a lone cyclone can threaten a continent with such a wide array of hazards, does it represent merely a powerful spring storm, or could it be a signal, a preview of what the coming season holds? At the heart of this unfolding story is a single, troubling figure: 986 millibars. This number, currently appearing in forecast models, represents the projected central pressure of a cyclone expected to impact the northern plains on April 23rd. It is a value that demands our attention, for it is a direct measure of the immense potential energy this system contains. A pressure reading this low is profoundly out of place in late April, belonging instead to the powerful, tightly wound storms of January. These are the kinds of systems known for shutting down entire cities and causing widespread disruption, prompting meteorologists to use language typically saved for the harshest days of winter. And yet, this forecast value for a spring Thursday appears with a quiet certainty in the data, a stark anomaly against the gentle backdrop of the season. It is a number that seems to defy the calendar itself. To fully appreciate the significance of this figure, we can compare it to the norm. The average central pressure for a cyclone in this region during late April is typically a much gentler 1,000 to 1,004 millibars. This represents the ordinary, predictable rhythm of the atmosphere at this time of year, where weather systems form, bring some rain and wind, and then move on without major incident. The current forecast, however, deviates sharply from this familiar script. A reading of 986 millibars positions this storm within the lowest 5 to 10% of all recorded pressures for this season. This simple statistic tells a powerful story. For every 100 similar storms in the historical record, 90 to 95 of them have been weaker than the one now approaching. We are not observing an average event, but a true statistical outlier, a system operating at the far edge of what is considered possible for spring. This seasonal discrepancy is what makes the situation so potentially volatile, as pressure alone fails to capture the full picture. The danger of a classic winter storm comes from its combination of low pressure and the vast reservoir of cold air it commands. Late April, however, introduces a powerful new ingredient not found in such abundance during winter: atmospheric instability. With the lower atmosphere warming, moisture from the Gulf of Mexico surging north, and a higher sun angle aggressively heating the ground, the environment is primed with thermodynamic energy. When you place a system with the raw mechanical strength of a January cyclone into the supercharged setting of April, the effects are not merely additive, they are multiplicative. The atmosphere's response can become highly nonlinear across such boundaries, creating a feedback loop of escalating power. This is the core of the issue, and it helps explain why forecasters are viewing this event with a unique and complex mixture of confidence in the pattern and deep apprehension about its consequences. The true scale of this event becomes apparent when we consider its multifaceted and continental nature. This single cyclone is forecast to unleash not one, but 5 distinct types of hazards at the same time, a testament to its complexity and power. As meteorologists monitor the risk of tornadoes developing over the Central Plains, an entirely different threat emerges hundreds of miles away, where fire weather alerts are active across the southern high plains. There, extremely low humidity and strong downslope winds are creating conditions for dangerous, fast-moving fire behavior. Simultaneously, the storm's immense circulation will wrap cold air around its northern flank, drawing it into the Dakotas and Montana to generate blizzard conditions with heavy snow and severely reduced visibility. Further east, the upper Midwest faces a significant flood threat, driven by a convergence of saturated ground, melting snow, and another round of intense rainfall. And woven through all these distinct threats, a powerful wind field with gusts up to 60 miles per hour will stretch across 7 states, a hazard in its own right. One storm system, 5 distinct hazards, and a zone of active danger spanning 1,000 miles. Yet, if one signal within this complex forecast truly commands attention, it is a metric known as the Significant Tornado Parameter, or STP. The value for this parameter is predicted to reach 10, a number that warrants careful consideration and speaks volumes about the potential for severe weather. STP is a composite index, a single value derived from several key atmospheric ingredients that are known to foster the development of powerful, long-lived tornadoes. These ingredients include convective available potential energy, which is the raw fuel for a storm's intensity, and wind shear, the change in wind with altitude that imparts the critical rotation to supercell thunderstorms. It also incorporates storm relative helicity, which quantifies the available corkscrew spin in the lower atmosphere where tornadoes form. Finally, it accounts for the lifted condensation level height, indicating how low a storm's cloud base is a crucial factor for tornado formation and intensity. Normally, this combined value is well below 1. Readings above 3 suggest an environment capable of significant tornadoes, while values over 5 point to historically dangerous conditions. An STP value exceeding 8 is exceptionally rare in the historical record, making a forecast of 10 a profoundly serious indicator from the atmosphere itself. Thursday's forecast contains a number that has captured the full attention of the scientific community: 10. This is no typographical error, nor is it random model noise. It is a signal of immense potential, a value taken with the utmost seriousness. The reason for this intense scrutiny is what the Significant Tornado Parameter, or STP, truly represents. It does not predict that a tornado will occur. Instead, it indicates that the atmosphere holds the capacity to create one of the most violent tornadic environments ever observed, should all the necessary ingredients fall into place. The weight of this what-if scenario is profound, and it forms the very heart of our story. But this narrative extends far beyond a single day. Forecasters are not merely tracking one storm, but a persistent pattern unfolding over a 1-2 day period. They have already identified 3 distinct windows for severe weather, each separated by several days, yet linked by a deep, underlying atmospheric structure. This structure is acting like a relentless factory, poised to generate one event after another. The first window is set for April 23rd through the 24th, followed by a second from April 25th to the 28th. A third window, though viewed with less confidence, is beginning to materialize in the models around May 3rd to the 6th, too persistent to be ignored. This brings us to the central question, which is not what will happen on Thursday, but why the outcome remains so profoundly uncertain. Despite an environment that seems primed for catastrophe, the final result is far from decided. Forecasters are highly confident that a powerful cyclone will indeed form, and that severe weather will impact a vast area. What they cannot yet determine, however, is the character of that weather. Will Thursday be remembered for a single historic tornado? A storm discussed for decades to come? Or will the immense energy be scattered across 100 individual storms, causing widespread damage, but leaving no singular, defining scar on history? The environment itself is extreme, but the specific trigger remains elusive. It is in this space the gap between what the atmosphere is capable of and what it ultimately delivers that the true narrative resides. The atmospheric pattern developing over these next 12 days is more than just a fleeting weather event. It has the potential to define the entire 2026 severe weather season. This is not an isolated blip on the radar, but the initial pulse of a locked atmospheric regime. The reason this pattern is so persistent, why it will not simply dissipate after Thursday, is a story that grows more fascinating the deeper we investigate. To truly grasp where this is all headed, we must first understand the fundamental nature of the storm itself. A cyclone with a central pressure of 986 millibars does not simply materialize in late April out of nowhere. Something had to build it, piece by powerful piece. We begin with a storm that feels like January, but is occurring in April. The first clue to its unusual behavior lies within the pressure gradient. When meteorologists examine a surface pressure map, they are interpreting a story told by isobars lines that connect areas of equal atmospheric pressure. The closer these lines are to one another, the steeper the change in pressure over a given distance. And it is this pressure difference that is the fundamental driver of wind. In a typical late April weather system, these isobars are usually. This might produce gusts of 20 or 30 miles per hour as the system passes, but nothing that constitutes a sustained wind threat. The cyclone being forecast, however, is entirely different. Its pressure gradient is projected to be so tight that it could generate sustained winds of 30 to 50 miles per hour over an enormous region, with even stronger gusts. The spacing of the isobars on the forecast maps resembles something from the depths of winter, not the middle of spring. It is a clear sign that the atmosphere is not adhering to the calendar. If we were to compare this pressure structure to a typical winter cyclone, we would find many similarities. The central pressure would be comparable, as would the radial wind field and the overall geography of the airflow. A winter storm of this magnitude would certainly cause major disruptions wherever it tracked, but its appearance would not be a surprise. Winter is, after all, the season when such powerful systems are climatologically normal. What makes Thursday's setup so truly anomalous is not merely the low pressure at its heart. The true anomaly is that all the atmospheric components feeding this system are operating in perfect synchrony, at peak efficiency, during a season that normally works to suppress such alignments. It's a perfect storm in the most literal. The primary engine driving this entire system is the upper-level jet stream. At this moment, the jet stream is engaged in a performance it reserves only for its most dramatic displays, producing a jet streak of approximately 130 knots across the central United States. A jet streak is more than just a fast-moving ribbon of air. It is a specific dynamic feature that generates regions of divergence. In these areas, the atmosphere high above the ground is literally spreading apart, lifting air away from the surface below. When this powerful upper-level divergence is positioned over a developing surface cyclone, it functions like an atmospheric vacuum. Air is evacuated from the top of the storm column faster than it can be replaced from the sides, causing the surface low to deepen dramatically. This is the very mechanism of rapid intensification, and for this particular cyclone, it appears to be operating at maximum capacity. Another crucial element is the trough, the southward dip in the jet stream that often precedes the formation of a cyclone. This feature is also behaving in a way that accelerates the process, undergoing what meteorologists refer to as a negative tilt. As a trough travels eastward, it can rotate from a neutral alignment into a configuration where its southern end lags behind its northern end, creating a distinct backward lean. This negatively tilted shape serves to dramatically enhance the lifting dynamics on the eastern flank of the trough, precisely where this cyclone is forecast to be on Thursday. While a negative tilt is not exceptionally rare on its own, its combination with a 130-knot jet streak and a surface low already deepened to 986 millibars creates a celestial alignment of atmospheric factors. This is a constellation that seldom assembles in late April without a significant event to follow. The storm's initial formation is a process known as Lee cyclogenesis, with the Rocky Mountains playing an essential role. As air flows over the mountain range and descends on the eastern side, it is stretched vertically. The fundamental physics of rotating fluids dictates that this stretching motion generates cyclonic spin at the surface. In this way, the Rockies act as a vast storm factory, built directly into the continent's geography. Whenever a potent shortwave of energy traverses the Rocky Mountains, it carries the possibility of birthing a new low-pressure system on the eastern slopes. But the event unfolding this Thursday is unlike most instances of cyclogenesis. The shortwave arriving over the Rockies is already exceptionally energetic, and it is moving into an atmosphere perfectly configured to magnify its power in three distinct, compounding ways. We have already considered the role of the jet stream dynamics, which provide the upper-level steering and energy. This is the first powerful ingredient. The second is the influence of the mountains themselves, the orographic effect, which imparts an initial spin to the air, deepening the system through the mechanism of Lee cyclogenesis. A third and crucial factor is the release of latent heat. As thunderstorms ignite within the cyclone's warm sector, they will inject tremendous heat into the middle layers of the atmosphere. This added heat reduces the weight of the air column above, further lowering the surface pressure. In this way, the storms developing on Thursday will be actively strengthening the very system that created them. It is a self-perpetuating cycle, a feedback loop that meteorologists have already accounted for, which is why their confidence in the cyclone's ultimate intensity is so high, even as the specific threat of tornadoes remains uncertain. Normally, late April presents a different atmospheric picture. The thermodynamic energy is often not matched by such powerful dynamic support. In a more typical scenario, you might find immense instability building as the sun strengthens and the Gulf of Mexico sends warm, moist air northward. But the jet stream dynamics that provide the trigger are usually weakening as winter's influence fades. It is a situation of having abundant fuel but lacking the spark in the upper atmosphere. Conversely, a strong upper-level system might arrive, but before the surface layer has warmed enough to generate the instability needed for severe storms. The two essential ingredients rarely reach their maximum potential at the same time this late in the season. What makes this week so extraordinary is that they are both present, and both are at their peak. The cyclone's warm sector is drawing its power from a deep reservoir of moisture from the Gulf of Mexico, which is streaming north in a channel of southerly winds ahead of the main system. Across Oklahoma and Kansas, surface dew points are predicted to climb into the low to mid 60s Fahrenheit by Thursday afternoon. This level of moisture loading is a key indicator of the potential for explosive instability. When this rich moisture is combined with the heating effect of a late April sun, the resulting values for convective available potential energy or CAPE become enormous. The atmosphere is essentially storing vast reserves of power in its lowest kilometer, and the central question that defines this entire unfolding story is precisely where and when that stored energy will finally be released. This is the critical insight that can be lost when viewing this merely as a strong storm. This system doesn't just possess deep pressure, or powerful dynamics, or abundant moisture. It possesses all of these elements simultaneously, in a state of mutual amplification that elevates it from significant to potentially historic. The cold core dynamics of the upper-level system, which govern the jet stream and the pressure gradient, are merging with a warm sector that is charged with the full instability of late spring. Meteorologists have a term for this: dual-mode amplification. The system is being forced from the top down by the jet stream, and simultaneously from the bottom up by the release of instability at the surface. Each process feeds the other, resulting in a system whose mechanical structure resembles that of a midwinter storm, but whose thermodynamic fuel is that of late May. It is a rare and potent hybrid. This unusual combination prompts a question, one that must be approached with care and appropriate uncertainty. Are we beginning to see more of these hybrid systems? Are we witnessing events where the traditional boundaries between seasons seem to blur, where winter-level dynamics intrude upon spring environments, or where spring's instability arrives well ahead of its climatological schedule? The honest answer is that the science of attribution is profoundly complex. And this is not the place to resolve such a deep inquiry. But the pattern itself deserves acknowledgement. The observation that a storm with a January structure is occurring in late April is not a minor detail. It is the fundamental anomaly that defines this entire event. And so, the stage is set. The powerful dynamics are in place. The moisture is arriving. The jet stream is aligned. The trough is negatively tilted, and the process of Lee cyclogenesis is well underway. All the necessary components for a major event have been assembled. But knowing the engine is powerful does not tell you where the vehicle will travel. The geography of initiation, the specific zones where this system will concentrate its most extreme energy, is a different and far more uncertain story. That story begins at a location that meteorologists know by a very specific name, a place where three distinct atmospheric boundaries converge, creating a single zone of maximum potential. At this moment, that location is centered directly over Kansas and northern Texas, a feature known as the triple point. Every major severe weather event has a geography, and this one has a very specific address. Somewhere along a line, stretching through central Kansas and curving down into northern Texas, three separate atmospheric boundaries are converging into a single zone of immense atmospheric tension. To grasp why this convergence is so critical, we must briefly examine each of these boundaries. The warm front marks the leading edge of the warm, moist air streaming northward from the Gulf. It is a sloped surface that lifts the air above it, forming clouds as it advances, stretching roughly east to west. The cold front is the sharp, advancing edge of the cold air that the cyclone is pulling southward, a boundary where temperature, humidity, and wind direction change abruptly over very short distances. And finally, there is the dry line, a feature particularly common in the central United States. It is a north-south boundary, separating the humid Gulf air to its east from the hot, dry continental air flowing from the elevated terrain to its west. The precise location where all three of these boundaries intersect is known as the triple point. This is not a metaphor. It is a literal, geographic point where the warm front, cold front, and dry line all meet. In the entire country, it is the single most dynamically favored location for the initiation of storms. The reasons for this are almost elegant in their simplicity. At the triple point, you have intense moisture convergence from the dry line, which forces the unstable Gulf air upward into the zone, providing the final, critical trigger for development. The atmosphere is a complex engine, and on this day, two distinct frontal systems, a warm front and an approaching cold front, are providing the lift needed to release a vast reservoir of instability. This convergence creates a zone of maximum wind shear, where the transition between three different air masses compresses the change in wind speed and direction over an exceptionally short distance. Adding to this potent mix are mesoscale boundaries, smaller atmospheric features that can act as local triggers, focusing the initiation of storms into a very specific region. This entire setup creates what meteorologists call a triple point, and on this particular Thursday afternoon and evening, it is projected to settle over the corridor stretching from Kansas to northern Texas. It is no mere coincidence that this exact area maps almost perfectly onto a region showing significant tornado parameter, or STP, values near or even above 10. The triple point is, in essence, a natural STP maximizer, concentrating every critical ingredient that the index measures into a single geographic zone. The formula for this severe weather is remarkably complete. High levels of convective available potential energy, or CAPE, are being drawn northward by moisture from the Gulf. The convergence of air at the boundaries is generating high shear. Rapidly rotating winds in the lowest levels of the atmosphere are producing high helicity. And finally, high surface dew points are leading to a low lifted condensation level, meaning storms can form more easily. In this environment, everything that needs to be high for severe storms is high, and everything that needs to be low is low, all in the same place at the same time. But this triple point configuration has another effect, one that is less intuitive, but arguably far more significant. An environment like this tends to produce fewer storms, but each one possesses a much higher individual intensity. This outcome is the opposite of what one might casually expect. More atmospheric energy does not always translate to more storms. In convective meteorology, the concentration of that energy matters more than the raw quantity. The most powerful tornado-producing storms, known as isolated supercells, are rotating thunderstorms that need space to organize and strengthen. To reach their full potential, they must be able to process the surrounding wind shear and moisture without interference from neighboring storm cells. When too many storms develop in close proximity, they begin to compete for the available instability. Their outflow boundaries can disrupt each other's inflow of warm, moist air, and they often merge into linear systems. While these lines of storms are efficient at producing damaging straight-line winds and large hail, they are generally less proficient at spawning tornadoes. The triple-point environment, by limiting the number of initiation points, helps to keep storms isolated for longer periods. And history has shown that isolated storms forming in environments with STP values above 8 are the ones that can lead to the most memorable and destructive weather events. Adding another layer of complexity is a secondary low-pressure system that warrants close attention. While the primary surface cyclone will be centered over the central to northern plains, this secondary low is expected to form along the dry line near the border of Oklahoma and southern Kansas. Such features are common in major cyclone events, but its presence here is particularly significant because it acts as a local enhancer of convergence. This secondary low creates additional atmospheric lift in its immediate vicinity, providing another focusing mechanism for storm initiation that is separate from the primary cyclone. The precise location where this secondary low develops will be a key point of disagreement among weather models leading into Thursday. Even small errors in its predicted position, on the order of 50 to 100 miles, could shift the zone of highest risk considerably. The timing of this entire setup is also deeply connected to a phenomenon known as the late day alignment. The atmosphere undergoes a daily energy cycle. Late afternoon typically represents the peak of this cycle, as hours of solar heating have allowed the boundary layer to accumulate its maximum instability. Simultaneously, the dynamics of the jet stream, which operate on a much longer timescale, continue to evolve and strengthen throughout the day. On this Thursday, models are projecting that the moment of peak instability will align with the moment of peak shear sometime within the 9 to 10 p.m. Central Time window. This late alignment introduces two significant complications. The first is that nighttime tornadoes are substantially more dangerous. People cannot see them coming, and even with modern radar providing adequate warning times, fatality statistics for nighttime events are consistently higher. The second complication is that the verification of storm initiation and storm type will have to occur in the dark, limiting visual confirmation from storm observers and adding another layer of uncertainty to real-time forecasting. This is where the central question of this event reappears with full force. The triple point environment is maximally favorable. The ingredients are assembled, and the geography is focused. But will the storms actually fire in the right place, at the right time, and in the right mode? The model guidance is not in full agreement on the timing of initiation. In a setup that peaks so late in the evening, a disagreement of even 2 or 3 hours can be the difference between discrete, powerful supercells forming in darkness and a more consolidated linear system that has already swept through the area. There is no forecast tool in existence that can resolve that kind of disagreement with perfect confidence 1 to 2 days in advance. The human forecasters at the Storm Prediction Center are well aware of this, and the language in their outlooks reflects it, carefully phrased, heavily conditional, and loaded with probabilities that acknowledge the extreme possibilities on both ends of the spectrum. The triple point is a trap, in both the best and worst sense of the word. It traps atmospheric energy, concentrates it, focuses it, and prepares it for a dramatic release. However, the precise mechanism of that release, the specific chain of events that determines whether one supercell or 20 storms will fire, first remains beyond the grasp of deterministic forecasting. Understanding this uncertainty is not meant to dismiss the threat. On the contrary, it is to understand that the real danger in this setup is not reduced by the forecast uncertainty in a specific and troubling way. It is amplified by it. The STP value of 10 is the number that signals this extreme potential, and that number has a history worth knowing. There is a specific category of atmospheric measurement that forecasters treat with a unique level of respect, and significant tornado parameter values above 8 belong firmly to that category. To be precise about what an STP value of 10 truly represents, it is helpful to understand where that number sits in the historical distribution of all STP values ever computed over the United States. The vast majority of days in any given year see STP values near 0 across most of the country. Values that climb above 1 begin to correlate with environments capable of producing significant tornadoes, which are defined as those rated EF2 or stronger. As values rise above 3, they move into a territory associated with historical tornado outbreaks. This context is crucial for understanding what lies ahead. When meteorologists evaluate the atmosphere's capacity for severe weather, they often turn to tools like the Significant Tornado Parameter, or STP. On this scale, values exceeding 5 signify an environment that can support the most dangerous types of tornadoes recorded in modern history. Should these values climb above 8, they enter a rare category, representing approximately the top 1% of all observed STP environments. These are not merely theoretical maximums. They are real-world conditions that, while infrequent, leave an indelible mark on the historical record. For instance, the environment on April 27, 2011, the central day of the deadliest tornado outbreak in the contemporary United States, saw STP values reach this upper echelon across Alabama and Mississippi. Similarly, the 2013 Moore, Oklahoma tornado, an EF5 wedge that carved a mile-wide path of destruction, formed within this same tier of atmospheric parameters. Mentioning these events is not intended as a prediction, but rather as crucial context for why the forecasting community regards an STP of 10 with such profound seriousness. It is here, however, that a vital distinction must be made, separating careful scientific communication from simple fear-mongering. The STP is an environmental index, a measurement of the atmosphere's potential times to foster violent tornadoes if supercell thunderstorms can form and sustain their discrete structure. It is not a forecast that storms will occur, nor is it a direct prediction of tornadoes. Instead, it measures the room the atmosphere has created for a violent outcome. Should the convective process unfold in a very specific manner. The common analogy of a loaded weapon is particularly apt. A weapon with ammunition and a clear barrel is objectively dangerous, but it cannot fire unless a trigger is pulled. In the atmosphere, that trigger is storm initiation along a boundary like a dry line, with the correct mode and spacing a variable that the STP index does not and cannot measure. Given this, there are two fundamental ways that a forecast with extreme STP values can fail to produce a significant tornado outbreak. The first scenario involves what is known as cap failure in the wrong direction. The cap is a layer of convective inhibition, a temperature inversion that acts as a lid, preventing storms from developing. If this lid remains too strong throughout the evening, no storms may fire at all. While this might sound like a beneficial outcome, a cap that suppresses storms all day can break catastrophically during the overnight hours. This can release all of the accumulated instability at once, in a region where public awareness may have already started to wane. The second failure scenario is storm clustering. If storms initiate too early or too close together, they can generate a pool of cold air at the surface that undercuts the very environment needed for tornadoes. When this happens, the storms tend to merge from discrete supercells into a squall line, causing their tornado efficiency to drop dramatically, even as the potential for widespread wind damage remains high. The path to a successful tornado-producing scenario, on the other hand, is simpler to describe, but far more difficult for the atmosphere to achieve. It requires one or two isolated supercells to ignite along the dry line, right within the window of peak atmospheric shear. These storms must then maintain their unique, individual structures long enough to establish strong, organized rotation within their core. For the kind of long-track tornadoes that can travel for dozens of miles, this continuous rotation, or mesocyclone, must be sustained for a minimum of 30 to 45 minutes. This delicate process demands that the supercell remains undisturbed by neighboring storms or other atmospheric boundaries. It is a rare convergence of precise conditions, which explains why most severe weather setups, even powerful ones, do not result in such devastating outcomes. Adding another dimension to this complex risk is the element of timing. Current models project the maximum STP values to occur within the 9 to 10 p.m. Central Time window. This timing is critical, as it means that if discrete supercells do manage to form during this peak period, they will be traversing the landscape after dark. While nighttime supercells are not inherently stronger than their daytime counterparts, the danger they pose to human life increases significantly. This has nothing to do with storm physics and everything to do with human behavior. At night, people are at home and many are asleep. The crucial visual cues that allow someone to spot a developing tornado in daylight, such as a wall cloud or a funnel, are completely absent at 10 p.m. Although warning systems are effective, they are not perfect, and data shows that nighttime events have statistically higher fatality rates, particularly for vulnerable groups like the elderly, those in manufactured housing, and communities with limited access to warnings in their language. One final layer of complexity is the variability of dry-line mixing. Throughout the afternoon, solar heating causes the lower atmosphere to mix vigorously. This mixing can have two opposite effects on the dry line. It can either sharpen the boundary, which concentrates the moisture contrast and makes it a more effective trigger for storm initiation, or it can diffuse the boundary. A diffused boundary smears the moisture gradient across a wider zone, reducing its effectiveness as a focal point for storms. Model guidance currently shows disagreement on exactly how this mixing process will play out, and that disagreement is a crucial piece of the puzzle. A sharp, well-defined dry line is a far more reliable initiation boundary, and this uncertainty is one of the primary reasons that even experienced meteorologists are offering a range of probabilities for supercell development. We are therefore left with a powerful number, a 10 on the STP scale, that represents one of the most dangerous atmospheric environments in the historical record, yet it exists within a setup that cannot guarantee the trigger needed to unleash its worst possible outcome. This tension between extraordinary potential and genuine uncertainty is not a flaw in the science. It is the science. It is the honest, unvarnished truth of how our planet's atmosphere works. A constant and humbling dialogue between immense power and profound unpredictability. The true significance of this weather event lies beyond the raw data, in the story that the numbers tell and the one they do not. To grasp its sheer scale, we can trace a mental map of the United States. Imagine a vast circle stretching from the Texas Panhandle north to southern Canada, and from the foot of the Rockies to the Mississippi River. This enormous area represents the footprint of a single weather system on a single day. Within this circle, 5 distinct and powerful hazards will unfold simultaneously, each a product of the same parent cyclone, and each posing a severe threat to life and property. While the potential for tornadoes often captures the most attention, and rightly so, the true measure of this system is its breadth. This is not merely a regional storm. It is a continental engine, with different parts producing different kinds of disasters depending on where one stands. Our journey begins in the southern high plains, across the panhandles of Texas and Oklahoma, and into southeastern Colorado. Here, to the west of the developing severe storm threat, a completely different atmospheric drama is playing out. Dry air, flowing down from higher elevations, is combining with exceptionally low relative humidity, which can plummet below 15% in the afternoon. This arid air is then whipped by sustained winds of 40 to 50 miles per hour. Such conditions prompt the most serious of alerts, fire weather watches and red flag warnings, which are never issued lightly. They signal a landscape where low moisture in the air and on the ground has created a tinderbox, where any spark could ignite a wildfire that moves faster than a person can flee. This raises a sobering point. The fire risk is not a secondary concern, but a distinct and parallel catastrophe unfolding in a different part of this system's domain. Shifting our focus northward into the Dakotas and Montana, the cyclone reveals another of its dangerous personalities. In the cold sector of the storm, where polar air is being drawn down from the north, the system is poised to unleash a full-blown blizzard. This is not just a moderate snowfall, but a specific combination of intense snow, near-zero visibility, and powerful sustained winds, creating treacherous whiteout conditions across the open landscape. The mechanism behind this is a classic cold sector wraparound. The cyclone's counterclockwise rotation pulls frigid air south on its western side, while simultaneously wrapping moisture from the warm sector back into this freezing zone. A feature known as the deformation zone will then concentrate this moisture into a narrow band, potentially producing snowfall rates of 3 to 4 inches per hour. While April blizzards are not unheard of on the northern plains, their occurrence, alongside a major tornado threat several states away, is a clear meteorological fingerprint of an extraordinarily powerful and complex system. As we move eastward into the upper Midwest across Wisconsin, Minnesota, Iowa, and parts of Illinois, yet another hazard emerges, this one driven by water. This region has been grappling with weeks of above-average precipitation, leaving the soil in many areas completely saturated. At the same time, the remaining snowpack from winter continues to melt, feeding even more water into a drainage system already strained to its limits. Into this precarious situation, the storm is forecast to drop an additional 1 to 3 inches of rain. In a normal spring, this amount might be absorbed without issue, but here it becomes a critical tipping point. With the ground unable to absorb any more moisture, This new rainfall will run off immediately into streams and rivers that are already at or above flood stage. It shows how a storm's impact is not just about the storm itself, but about the history written on the landscape it encounters. Beyond fire, snow, and flood, there is a fifth, more pervasive threat: the wind itself. This is not the turbulent wind of a tornado or a thunderstorm, but the vast, sustained wind field generated by the immense pressure gradient of the cyclone. A deep 986 millibar low-pressure system like this creates a powerful atmospheric engine that affects the air for hundreds of miles from its center. Across a 7-state area, from Wyoming to Wisconsin, sustained winds of 30 to 45 miles per hour, with gusts reaching 60 miles per hour, are forecast entirely independent of any storm activity. This means that even in areas with clear skies, the wind alone is strong enough to topple trees, damage structures, create hazardous driving conditions for large vehicles, and potentially disrupt power for hundreds of thousands of people. It is a reminder that the storm's influence extends far beyond the rain and clouds. So, what makes the United States so uniquely prone to these simultaneous, continent-spanning hazard events? The answer lies fundamentally in its geography. The orientation of North America creates the perfect conditions for atmospheric collisions in the spring. While the Rocky Mountains form a formidable north-south barrier that shapes airflow, there is no corresponding east-west mountain range to prevent what happens downstream. This open layout allows cold, dense polar air from Canada to surge southward, sometimes reaching all the way to the Gulf of Mexico. At the same time, warm, moist air from the Gulf can stream unimpeded northward into the Great Plains. When a powerful upper-level trough forces these two vastly different air masses to meet, the resulting clash is not a localized affair. It creates an enormous zone of conflict that can stretch for 1,000 miles across the flat terrain. This stands in stark contrast to a continent like Eurasia, where the massive Himalayas and the Tibetan Plateau form a definitive wall, often keeping tropical and polar air masses apart. The unique meteorological landscape of the central United States gives rise to a severe weather climatology unlike any other on Earth. This region's geography can act as a crucible for events like the one unfolding on Thursday, a reality that is both a source of endless fascination and a recurring cause of profound loss. We are witnessing what researchers call a compound hazard day, where multiple, distinct forms of extreme weather converge on the same area at the same time. This interplay creates risks that are far greater than the sum of their individual parts. Our emergency management infrastructures are built to handle one crisis at a time, not 5 simultaneously. How can evacuation routes for a flood zone remain viable when they are blocked by debris from high winds? How can fire crews battling blazes on the southern plains be redeployed to assist with blizzard rescues in the Dakotas? The logistical strain of such events pushes response capacity beyond its designed limits. This is merely the first day of a 12-day ordeal. If a weather system this vast, this complex, and this charged with energy is only the prelude, what will the cumulative effect be by day 12? To even begin to answer that, we must understand why the atmosphere does not simply move on. We must look higher, beyond the surface cyclone and the jet stream, to the grand, overarching wave structure that is holding this entire pattern in place. To visualize this process, one might imagine a factory that assembles weather systems. The raw materials, in the form of atmospheric energy, arrive from the Pacific Ocean. This energy is organized into disturbances known as short waves, compact zones of enhanced spin and lift carried within the broader flow of the jet stream. As these short waves journey eastward, their encounter with the Rocky Mountains triggers the process of cyclogenesis, giving birth to new surface low-pressure systems on the eastern slopes. In a typical atmospheric sequence, a short wave crosses the mountains and generates a cyclone. This storm then tracks northeast across the Central Plains, eventually departing into Canada or the Great Lakes region. The entire cycle resets over about 3 to 5 days, usually followed by a period of calmer weather before the next short wave arrives. It is a familiar and predictable rhythm. But the situation unfolding now is a profound departure from that normal rhythm. An atmospheric feature, known as the Pacific Shortwave Train, is delivering these disturbances to the western United States with unrelenting frequency, one arriving approximately every 48 to 72 hours. This means that before the cyclone generated by the first short wave has even had a chance to complete its journey, a second short wave is already crossing the Rockies, beginning the process of formation all over again. And before that second storm has run its course, a third is already at the door. The factory is no longer on a standard production schedule. It is as if it is running around the clock, with no time for reset or recovery. This phenomenon is described by the term pattern lock. The large-scale atmospheric arrangement over North America is not progressing through its usual sequence of weather regimes. Instead, it seems to be held in a fixed state by powerful, large-scale wave dynamics. This has resulted in the persistent establishment of a deep trough of low pressure over the western United States and a corresponding ridge of high pressure over the east. This specific configuration creates a stationary zone of maximum atmospheric conflict, the boundary where cold polar air from the west clashes with warm, moist air from the Gulf of Mexico and plants it directly over the Central Plains. There it remains, day after day, system after system. The computer models used for forecasting are showing a remarkable consistency in predicting this pattern for the next 12 days. This in itself is a significant signal. Extended forecasts typically lose reliability beyond a week as small uncertainties grow into large errors. When multiple models, which normally diverge from one another over a 10 to 1-2 day period, all point to the same fundamental configuration, it suggests the underlying large-scale pattern is exceptionally strong and stable. Meteorologists refer to this as a high signal-to-noise ratio. It grants a higher than normal confidence that multiple windows for severe weather will indeed open, even if the specific details of any individual storm remain uncertain. It is also crucial to understand that these are not truly independent storms, as a casual reading of a weather map might suggest. Each successive system inherits the environmental conditions left behind by its predecessor. For example, the soil moisture from a flooding event in the first system increases the amount of evaporation, feeding more available moisture into the next. The large-scale wind pattern, locked in place, continuously funnels this moisture northward from the Gulf. The atmospheric instability that is tapped by one storm does not have time to fully dissipate before the next system arrives to draw from it again. In a very real sense, these individual storms are not separate events, but rather successive releases from the same vast reservoir of atmospheric energy. This interconnectedness raises a subtle and somewhat counterintuitive question. If each storm partially uses, but does not completely exhaust the available moisture and instability, and if the pattern lock ensures a continuous resupply of both, could the environment actually become more efficient for storm generation over time? The moisture that evaporates from flooded ground after the first system can add to the total atmospheric loading for the second. The destabilized air may recover between events, but perhaps not completely. Even the outflow boundaries from previous storms can act as triggers for new ones. In short, the question of whether the later severe weather windows are more or less dangerous than the first is genuinely open. It is not a given that the threat will diminish. The conveyor belt metaphor, while useful, is ultimately incomplete. A factory's conveyor belt produces a series of identical items. This atmospheric conveyor belt, however, is producing dynamic systems that actively interact with the byproducts of the ones that came before. It is this complex interaction, this feedback loop between storms, that is the most challenging element of the 1-2-day pattern to model and to communicate. It introduces a profound uncertainty that lies at the very heart of this unfolding weather story. We will revisit the intricate dance between storms and the larger systems that birth them when we discuss the latent heat feedback loop. For now, however, a more immediate question arises. What is driving this atmospheric conveyor belt with such relentless momentum? The answer lies not in the weather we feel at the surface, but in the physics of the high atmosphere, on a scale that dwarfs our everyday experience. The jet stream does not trace a simple, clean path around our planet. It is not a placid river in the sky. Instead, it meanders and buckles, amplifying into vast, continent-spanning waves. These are known as Rossby waves, the fundamental wave structures that organize the atmosphere and oceans on a planetary scale. Their existence is a direct consequence of the changing influence of Earth's rotation, the Coriolis effect, as one moves from the equator toward the poles. When these waves have a small amplitude, the jet stream flows in a relatively straight west-to-east direction, a zonal pattern that allows weather systems to cycle through and move on. But when Rossby waves grow in amplitude, the jet stream contorts into dramatic north-south excursions, and the eastward progression of these immense waves slows to a crawl. An exceptionally amplified Rossby wave can become stationary, grinding to a complete halt. Such a stall is the foundational cause of the weather pattern currently locked over North America. The crucial detail is not merely that a trough has formed over the western United States, but that this trough is refusing to move. This is the very definition of a pattern lock, and it reveals the immense power these atmospheric structures hold. The deep, low-pressure trough lingering over the American West is one part of a Rossby wave that has amplified so much that its normal eastward momentum has been broken. This disruption involves a process known as wave breaking. In meteorology, this term describes a Rossby wave that has reached a non-linear limit, causing its energy to scatter rather than continuing to propagate downstream in a coherent fashion. The downstream consequences of this wave breaking are profound, leading to what is known as a blocking situation. The high-pressure ridge situated over the eastern United States, downstream of the Western Trough, is being continuously reinforced by the convergence of energy from this breaking wave. This makes the ridge exceptionally stubborn, a formidable barrier that resists the eastward march of weather systems. As cyclones are generated by the Western Trough, they track northeastward only to collide with this fortified ridge. The ridge then deflects them toward Canada, or redirects their energy, ensuring the fundamental architecture of a Western Trough and an Eastern ridge remains intact. As new short waves arrive from the Pacific, they encounter the same stationary trough, are amplified by the same dynamics, and generate new cyclones, perpetuating the cycle. This kind of persistent pattern can last anywhere from a few days to several weeks. Current models suggest a shorter duration, but the honest truth is that the exact lifespan of this pattern lock is one of the most uncertain parts of the forecast. What the models do agree on is that this configuration will not dissipate before the first two windows for severe weather have passed. Whether the third window, in early May, will unfold under this same locked pattern, or will see a transition to a new regime, is where forecast confidence truly begins to wane. This entire dynamic is critical to our central question. The Rossby wave stall is the mechanism that ensures the conveyor belt continues to run, guaranteeing that after Thursday's system, another opportunity for severe weather will arise in a few days, and perhaps another after that. But here lies a crucial distinction. Knowing the wave is stalled tells us nothing about whether an individual storm within that pattern will produce one catastrophic tornado or 100 forgettable ones. The large-scale dynamics set the stage. They do not dictate the local performance. In the gap between these two scales of knowledge, all meaningful uncertainty resides. To illuminate this gap, we must look to another piece of the puzzle, a subtle, hidden driver connecting the tropics to the mid-latitudes. Deep in the tropical Pacific, a signal is being generated that produces no tornadoes and no blizzards. It is invisible on any radar, yet its influence can be seen on the weather events unfolding across the United States. This signal is the Madden-Julian Oscillation, or MJO. It is a massive pulse of enhanced and suppressed rainfall that travels eastward around the equator, completing a full circuit in roughly 30 to 60 days. It is not a storm, but rather a slow-moving, organized wave of cloud and rain in the tropical atmosphere. Forecasters monitor the MJO's phase with great care because its position has a well-documented, though not perfectly understood, influence on the jet stream in the mid-latitudes. The current phase of the MJO is one that historically favors the development of a persistent trough over western North America. The tropical convection associated with this phase is located in just the right place to inject wave energy into the higher latitudes, reinforcing the very blocking configuration we have been discussing. This is not a simple, direct link, like one billiard ball striking another. It is a probabilistic reinforcement. The MJO does not command the jet stream. It merely shifts the odds, making certain configurations more likely. Right now, it is tilting the odds heavily in favor of the pattern already in place. Layered on top of this MJO signal is another large-scale pattern known as the Pacific North American Pattern, or PNA. The PNA is a mode of variability that describes the arrangement of high-pressure ridges and low-pressure troughs across the Pacific Ocean and North America. In its positive phase, it typically favors a ridge over the eastern Pacific and western North America, with a trough over the eastern part of the continent. In its negative phase, the opposite is true. The current PNA configuration has been identified by forecasters as one that also supports the locked trough pattern. When the influences of the MJO and the PNA are combined, they produce a powerful probabilistic forecast. This alignment suggests there is a 60 to 70% chance that the current atmospheric pattern will persist for at least the next 10 days. But what does a number like 60 to 70% truly mean in the face of nature's complexity? Understanding that figure clearly is essential to grasping the full story. A forecast that projects a 60 to 70% chance of severe weather over 10 days is not assigning that probability to each individual day. Instead, it indicates a high likelihood that the large-scale atmospheric pattern will remain locked in a configuration that supports severe weather opportunities. The actual formation of storms hinges on smaller, mesoscale factors that broad patterns like the MJO and PNA cannot foresee. Yet, the probability of this persistence tells us the atmospheric conveyor belt is more likely to keep running than to stop, and that the overall forecast structure is more likely to hold true than to break down. The study of these interactions between tropical and extratropical forces is a relatively modern field. Its rapid development over the last 20 years is a key reason that 1-2-day forecasts now provide more useful information than they did a decade ago, not by being precise, but by being directionally reliable, which is a more honest form of skill. There is a speculative element here worth considering. When multiple large-scale forcing patterns or teleconnections like the MJO and PNA align simultaneously, they may enhance the persistence of a weather regime. Some researchers refer to this as teleconnection stacking, the idea that reinforcing signals can create pattern locks that are more durable and extreme than any single force would produce. This is not established doctrine but an active area of research, and it helps explain why this 1-2-day window is so compelling to the forecasting community. What the alignment of the MJO and PNA guarantees is the structural persistence of this overarching pattern, What it cannot determine is how the energy within that pattern will actually be released on any given day at a specific location. That release is governed by mesoscale processes, the behavior of individual boundaries, atmospheric caps, and dry lines. It is shaped by the microscale interactions between convection and its environment, and ultimately by a degree of non-linear unpredictability that the atmosphere always holds in reserve. In this way, the alignment ensures the stage is perfectly set, but the performance itself remains unwritten. Beneath the surface of most weather reports, a profound conversation is taking place between storms and the larger systems that create them. A developing thunderstorm does not simply act as a passive consumer of the atmospheric energy around it. On the contrary, it actively reshapes its own environment. The most physically significant of these modifications is the release of latent heat. As water vapor rises and condenses into cloud droplets, and as that liquid water then freezes into ice crystals, the energy originally used to evaporate the water is released back into the atmosphere. This energy does not simply vanish. It is deposited directly into the mid-levels of the troposphere, warming the air column at altitudes between roughly 15,000 and 30,000 feet. This seemingly local process has consequences that ripple far beyond the individual storm. Warming at these middle altitudes in the atmosphere reduces the air pressure at the surface, directly beneath and around the storm, because warmer air is less dense and exerts less weight per unit area. When a large cluster of thunderstorms or an extensive area of convection releases latent heat all at once, the collective mid-level warming becomes significant enough to measurably deepen the surface low-pressure system tied to the frontal system. Here we see a critical feedback loop. The cyclone does not merely drive the storms, in turn, drive the cyclone. This process, known as diabetic deepening, is not a negligible secondary effect. It is one of the primary mechanisms by which rapidly intensifying cyclones can deepen faster than the purely dynamic components of the jet stream and trough would predict. For the 1-2 day pattern, this feedback loop operates on a scale that transcends any individual storm day. As each successive shortwave crosses the Rockies and generates a new cyclone, the convection that fires along the warm sector of that cyclone releases vast amounts of latent heat into the mid-levels. That added heat warms the air aloft, which strengthens the downstream ridge and simultaneously deepens the upstream trough. A stronger downstream ridge is a more effective block against the eastward propagation of the trough, which extends the pattern lock. A deeper upstream trough, in turn, becomes a more energetic source region for the next shortwave. The result is a system that is, in a thermodynamic sense, partially fueling itself through its own convective output. This is not a perpetual motion machine. The energy ultimately traces back to the sun's heating of tropical and subtropical ocean surfaces, which drives the evaporation that loads moisture into the atmosphere in the first place. But the feedback loop means that the 1-2 day pattern is not simply running on a fixed energy budget that depletes over time. It is interacting with its own outputs in ways that can sustain or even amplify the activity beyond what the initial large-scale forcing alone would produce. The moisture transport from the Gulf of Mexico is the critical link in this entire chain. As long as the large-scale wind pattern continues to direct southerly flow across the Gulf and into the central United States, fresh moisture is continuously available to fuel the next cycle of convection. Each storm taps the moisture, converts it to precipitation, and releases the latent heat. Then, evaporation from saturated soils and recovering vegetation partially recharges the low-level moisture content for the next event. The moisture pool does not fully recover between events, but it does not fully deplete either. It operates in a kind of dynamic equilibrium that keeps the thermodynamic forcing available for successive systems. This raises a careful but profound question. Could this feedback mechanism extend the pattern's duration beyond what the large-scale forcing alone would predict? The Rossby wave stall determines the structural persistence of the trough's configuration. The MJO and PNA alignment modify the probability of that persistence, but the latent heat feedback from the convection itself may be providing an additional reinforcement mechanism that prolongs the locked state. If this is the case, then the three-window forecast might be conservative. There could be a fourth window. There could be a fifth. This is speculative, a humbling reminder of the intricate, self-reinforcing systems that govern our planet's atmosphere. At present, forecast models do not indicate a fifth distinct window for severe weather. Beyond the 1-2 day horizon, the inherent uncertainty in our predictive tools becomes so significant that forecasting the development of specific storms is no longer a meaningful exercise. However, the underlying physical mechanisms that could sustain an extended period of activity are very much in place. The possibility that the atmosphere is reinforcing its own pattern through convective feedback is not merely a theoretical curiosity. It may have profound implications for what unfolds beyond the 1-2 day window this story focuses on. What is most critical for understanding the narrative unfolding before us is the role of latent heat feedback. This process confirms that the 1-2 day pattern is far from a passive series of independently triggered storms. Instead, it reveals an active, partially self-sustaining cycle, a kind of conversation between the storms and the larger atmospheric system. And yet, despite all this feedback and amplification, a fundamental question remains unanswered. Whether any single event in this sequence will unleash concentrated catastrophe or result in more dispersed, lesser impacts is as uncertain as ever. The macro-scale physics are working to perpetuate the pattern. But it is the micro-scale physics that will ultimately determine the character of each storm. Part 10. The 1-2 day compression hypothesis. Let us consider a different way of conceptualizing time in meteorology. A typical period from late April through early May might, in historical terms, feature one or two significant severe weather outbreaks. These would usually be separated by quiet intervals, lasting several days or even a week. Across a 20 to 5-day window, we might see 3 or 4 days with marginal severe weather potential over the central plains. In this more conventional scenario, active days are interspersed with calm ones. The total accumulated severe weather activity, measured by confirmed tornado reports, significant wind events, and documented large hail, is distributed across a month. This distribution allows for recovery, both in the atmospheric sense of recharging and in the practical human sense of emergency response and community rebuilding. What the current 1-2 day pattern seems to be doing, however, is something far more intense. It appears to be compressing all of that expected activity into a dramatically shortened time frame. The prospect of 3 severe weather windows in just 12 days, with the potential for a fourth if the pattern persists, represents an unusual clustering of convective events. This is remarkable even for April and May, which are historically the most active months for severe weather in the central United States. This sustained threat is supported by one of our most reliable long-range forecasting tools, the European Centre for Medium-Range Weather Forecasts model. Its guidance shows the locked trough configuration remaining in place through at least the beginning of May. Furthermore, multiple ensemble members, the individual model runs that account for uncertainty by using slightly different starting conditions, are indicating configurations favorable for severe weather on several days. Throughout this period, this raises a critical question about the nature of risk itself. The concept of temporal clustering, where extreme events are bunched together in a compressed window instead of being spread out over time, is a subject of growing interest for researchers studying climate variability. When individual events strike in rapid succession, without any quiet periods in between, the cumulative risk is not simply additive. Infrastructure damaged by a first event becomes more vulnerable to a second. Emergency resources deployed for one response are less available for the next. Communities that have not yet completed damage assessments or received follow-up warnings from the first storm are ill-prepared for another. The psychological and organizational strain from repeated, rapid-fire events is a real and measurable phenomenon. The rarity of such an extended sequence of slight-risk days, the formal designation from the Storm Prediction Center for a broadly elevated severe weather threat, is also worth noting. While several consecutive slight-risk days are not unheard of during active spring seasons, having them interspersed with enhanced risk and moderate risk designations across a 1-2 day period would signify an unusually sustained and active pattern. The forecast products being issued by the SPC reflect a deep concern not just about individual storms, but about the sequence as a whole. This forces us to consider the broader context of what we are witnessing. The climate context for this event requires careful and precise framing. There is an active scientific debate about whether the frequency of certain extreme weather events is changing, and specifically, whether temporal clustering of severe weather is on the rise. The evidence remains mixed, and detecting clear trends against the backdrop of natural weather variability is a significant statistical challenge. Therefore, this analysis will not claim that the current 1-2 day pattern can be attributed to any specific long-term trend, as the attribution science does not yet support such a definitive link with confidence. What can be stated honestly is that the physical mechanisms driving this type of event specifically, the amplification of Rossby waves and the formation of blocking configurations, are subjects of ongoing research into whether their frequency and persistence are changing. The current event serves as a data point in that research, not a final conclusion. Ultimately, the 1-2 day compression hypothesis suggests that the significance of this pattern has a temporal dimension as well as a geographic one. Even if no single storm within this window achieves historic levels of devastation, the combined effect of multiple events in rapid succession could produce an aggregate outcome that rivals or even exceeds that of a single major outbreak. The cumulative damage, disruption, fatigue, and depletion of resources represent a different kind of disaster, one that is less dramatic and less photogenic, but no less real in its consequences. The atmospheric pattern is loaded. The compression of time is real. What happens next, in the corridor from central Kansas to North Texas on Thursday night, will be the first test of how this 1-2 day story begins to resolve. The critical questions remain. Where exactly will the storms ignite? How will they evolve? And which destructive mode will the atmosphere ultimately choose? The answers will arrive in windows. Part 11. Window 1, April 23rd through 24th, the test case. On Thursday, the story becomes personal. The initiation sequence on April 23rd will not unfold uniformly across the entire high-risk area at once. Instead, it will be a localized and highly specific series of events, a test case for the powerful atmospheric dynamics at play. The unfolding story of this weather system begins in the early afternoon, with storm development anticipated across the northern tier. Specifically, regions of South Dakota and Nebraska will likely see the first cells ignite, as the day's surface heating and approaching atmospheric dynamics become strong enough to erode the morning's convective inhibition, a stable layer of air, often called the cap. The significance of these initial storms lies not in their own immediate threat, but in their potential to influence the environment far downstream. This raises a crucial question of atmospheric interaction. These northern storms can generate pools of cold air that spread southward, altering the delicate balance of moisture and stability across Kansas and Oklahoma. This interaction is one of the greatest sources of uncertainty in Thursday's forecast. as those southern regions require an undisturbed environment to realize their own severe weather potential during the evening hours. If the storms over South Dakota and Nebraska grow sufficiently vigorous and widespread, their cold outflow could fundamentally reshape the thermodynamic profile over central Kansas by late afternoon. Such an event would dampen the instability precisely in the area, and at the time when models project significant tornado parameter, or STP, values approaching 10. This type of mesoscale interaction is notoriously difficult for both regional and national models to predict, as it hinges on storm behavior that cannot be known in advance. Some simulations suggest these early storms will remain relatively weak, producing only modest cold pools that fail to contaminate the southern environment. Other model runs, however, show them becoming more organized, launching outflow boundaries that surge south and shift the critical dry line position within Kansas. It is a delicate balance, where events hundreds of miles away could decide the fate of the evening. As daylight fades, the primary focus will shift to Oklahoma, particularly to a triangular zone connecting the Oklahoma City metropolitan area, the Wichita Falls area to the southwest, and the Tulsa region to the east. This is the region where models predict the highest STP values will align with the window of peak wind shear. Consequently, it is the zone that the Storm Prediction Center and local National Weather Service offices will be monitoring with the most intense focus. Should storms initiate here, in a discrete, isolated mode, the central question of this entire event finds its most extreme potential answer. The theoretical worst-case scenario, a single, powerful supercell tracking northeastward from central Oklahoma through the evening, maintaining its structure within a 130-knot jet stream and an environment with an STP of 10, would be realized. However, even in such a potent environment, there is a natural tendency for storms to cluster together, creating a genuine dilemma for meteorologists and storm chasers alike. The choice becomes a difficult one. Does one position for the rare but potentially catastrophic discrete supercell, thereby risking proximity to the most violent possible tornado? Or is it wiser to prepare for the statistically more probable scenario of a linear storm system, which demands a completely different geographic strategy? This is not merely a recreational or academic question. For anyone within the risk zone, it is a matter of life and safety, as the two outcomes necessitate different preparedness actions. Discrete supercell tornadoes are often easier to track individually on radar, allowing for more specific warnings with relatively accurate paths. In contrast, tornadoes embedded within linear systems, such as squall lines, can form with very little warning, making them harder to issue precise alerts for, and more dangerous for those in vehicles or manufactured homes. The timing of this event, under the cover of darkness, deserves its own moment of honest consideration. If the peak storm development indeed arrives within the 9 to 10 p. window, the public preparedness situation changes fundamentally compared to a late afternoon event. By this time, children are often in bed, and adults who might have been monitoring weather apps at 6 p.m. may have gone to sleep. The social amplification of warnings, which relies on community networks to spread the word, is significantly slower and less reliable at night. While the National Weather Service offices covering this region are acutely aware of this challenge and will be communicating proactively, the effectiveness of any warning hinges not just on its issuance, but on its receipt and the subsequent action taken. And as data shows, nighttime receipt and action rates are measurably lower than those during the day, posing a profound challenge to public safety. In the grander scheme, Thursday is not just an isolated event. It is the first critical data point in what could be considered a 1-2-day atmospheric experiment. How the atmosphere chooses to release its stored energy on this day, whether it concentrates its power into a few violent, organized structures or disperses it across a broad area, will provide invaluable information. This data will help the forecasting community calibrate its expectations for two subsequent windows of potential activity. The atmosphere itself does not learn from its own behavior, but the meteorologists who study it certainly do. The verification of Thursday's forecast, whatever the outcome, will serve to refine the envelope of uncertainty for whatever comes next. To truly grasp the day's potential, one must understand the invisible battle fought within the atmosphere long before any storm appears on radar. This is a war of storm modes, waged between competing physical processes. On one side are the ingredients that favor the formation of discrete supercells. Strong directional wind shear in the lowest kilometer of the atmosphere provides the spin necessary for tight, rotating mesocyclones to form within isolated storms. High values of convective available potential energy, or CAPE, concentrated in a narrow corridor, support the tall, powerful updrafts that can sustain this rotation. Furthermore, low lifted condensation level heights, projected to be in the 300 to 500 meter range over Oklahoma, bring the cloud base closer to the surface. This reduces the distance a tornado must stretch to reach the ground, making its formation more likely. A sharp, well-defined dry line acts as a focus trigger, limiting the initial number of storms and allowing them to remain separate. All of these factors are aligned in favor of discrete supercell development. Fighting against this potential, however, is the physics of cold pools. Every thunderstorm, as it produces rain, also generates a downdraft of cooler, denser air. When this downdraft hits the ground, it spreads out, creating a boundary of cold, stabilized air, known as a cold pool or an outflow boundary. These are not inherently destructive to a storm. A powerful supercell's rotation can allow it to continuously draw in fresh, unstable air from ahead of the advancing cold pool. But the storm's own creation can become its undoing. If the cold pool activity becomes too aggressive, driven by an especially vigorous downdraft or slow storm motion that allows the cold air to expand rapidly, it can surge forward and undercut the very inflow of warm, moist air that the storm needs to maintain its life-sustaining rotation. This self-limiting process represents the other possible outcome in this atmospheric war, where storms choke on their own cold exhaust, leading to a less focused, more widespread threat. When several storms begin generating their own cold pools at the same time, a critical process unfolds. These pools of cool, dense air can merge, forming a vast, stabilized region at the surface. This effectively suffocates the individual, discrete storms, forcing them to organize into a linear structure known as a squall line. This transformation from a supercell to a squall line is remarkably swift, often occurring in just 20 to 40 minutes. In this brief window, the entire character of the severe weather threat changes. While a squall line can still produce tornadoes, they are generally weaker, shorter-lived, and far more difficult to anticipate than those from a supercell. They arise from different mechanics, typically from mesovortices along the line's leading edge, and lack the clear visual or radar warnings of a supercell's classic hook echo. Instead, a squall line's primary threat is often widespread, long-lasting wind damage from its bowing segments, which can affect huge areas without creating the focused, catastrophic ruin of a single, violent, long-track supercell tornado. The atmosphere, in essence, is presented with a choice, and it makes this decision based on processes that operate at scales far too fine to be resolved by modern forecast models. The outcome of an entire severe weather event can hinge on these unseen details. The precise humidity profile within the boundary layer over central Oklahoma at 5:00 p.m., the exact location of a cold pool boundary left behind by a storm cluster in Nebraska 6 hours earlier, or the specific orientation of the dry line at the moment the first storm ignites. It also depends on whether that initial storm can remain isolated long enough to establish itself as a dominant mesocyclone before its neighbors can develop their own competing cold pools. This is the hidden reason why model forecasts showing identical large-scale parameters can yield radically different results. The model may see a significant tornado parameter of 10, a favorable wind shear profile, and storm initiation along a dry line, but it cannot resolve the micro-scale competition between storm cores. The outcome of that competition determines whether the day is remembered for a violent tornado tracking across 3 counties or for widespread damage scattered across a broad region with no single standout event. Meteorologists have a specific term for this kind of forecast challenge: high-end potential with mode uncertainty. This phrase elegantly captures the situation's dual nature. It acknowledges that the environment possesses the ingredients for extreme weather, while also admitting that the probability of actually realizing that potential depends on factors that cannot be resolved with certainty ahead of time. It is a testament to the honesty of the science. This is precisely why the Storm Prediction Center issues moderate and high-risk outlooks for such setups using carefully chosen conditional language. The question of storm mode does not have a deterministic answer until the atmosphere reveals its choice in real time. So, what is the most probable outcome in such a scenario? If we use historical analogues from similar atmospheric setups as a guide, the odds tend to favor a mixed mode event. This would likely begin with a period of discrete supercells during the early evening across Oklahoma and Kansas, followed by an evolution into a more linear structure as interactions between cold pools take over through the night. In that scenario, the tornado risk is certainly real, but more distributed. While the risk of widespread and significant wind damage is high. Yet, there remains a tail risk, the low probability but high-impact scenario, where a single supercell maintains its discrete structure through the window of peak environmental conditions. This possibility is real and cannot be forecasted away. It is simply less likely than the mixed-mode scenario. Part 13, Window 2, April 25th through 28th. This brings us to the reload. Before the discussion around Thursday's potential has even concluded, the next weather system is already making its way across the Pacific. A second short wave in the atmospheric train follows just a few days behind the first. As the initial cyclone tracks into Canada and its associated severe weather window closes, this second short wave approaches the Rockies, beginning its own process of cyclogenesis. This sets the stage for another round of significant weather. By Friday, the frontal boundary from the first window will have swept across most of the southern plains. The cooler, drier air mass behind it will then almost immediately be undercut by the next surge of moisture streaming north from the Gulf of Mexico. This moisture rides on the back of the retreating first cyclone and then on the leading edge of the developing second system. The atmospheric recovery is astonishingly rapid. By Saturday, the thermodynamics are already recharging, and by Sunday, the models begin to show a setup with instability and shear values that approach the dangerous parameters seen on Thursday. This reload phenomenon is one of the most alarming aspects of the current pattern lock for the forecasting community. In a typical severe weather season, a major outbreak is usually followed by a recovery period of 3 to 5 days. During this time, the cool, dry, and stable air brought in by the cold front is gradually replaced. The boundary layer needs time to replenish its moisture and instability, and the upper level pattern must cycle back into a configuration that can support another major system. Under the present pattern lock, however, that recovery time is dramatically compressed. The intrusion of cold air behind the first window is relatively shallow and short-lived, as the overarching pattern is already driving another surge of warm air northward. The return of Gulf moisture is forecast to be swift and substantial, with surface dew points expected to recover to near Thursday levels by Sunday or Monday. The period between April 27th and 28th is the primary focus of this reload. Current model guidance, examined by operational forecasters, shows the strongest signal for severe weather on Sunday. However, this second window presents some notable differences from the first. The projected storm track of the second cyclone is somewhat farther east, which shifts the zone of highest risk from Kansas and Oklahoma toward the Missouri, Arkansas, and Tennessee corridor. This is a fundamentally different geography for severe weather. The terrain is more complex, population density is higher in some areas, and the region's agricultural communities have a different infrastructure profile than those on the open plains. One of the most fascinating aspects of this second window is the idea of a preconditioned atmosphere. The soil across the new risk zone will already be saturated from the rainfall of the first system. This seemingly small detail can have a significant impact. A wet surface alters the local energy budget as it evaporates differently than a dry one. This process can maintain higher humidity near the ground, potentially accelerating the recovery of atmospheric instability. It's a feedback loop that adds yet another layer of complexity, suggesting the atmosphere may be even more primed for what is to come. The first weather system leaves behind a subtle but powerful legacy. Convection from prior storms creates outflow boundaries, while varying patterns of surface moisture and soil temperature etch invisible lines across the landscape. These remnants become part of the mesoscale environment that storms in the second system will encounter. It's a crucial detail, as these boundaries can serve as new triggers for storm initiation or act as zones that enhance wind shear, elevating the tornado risk in areas that larger synoptic models might not identify as primary threats. This is the cumulative environmental effect in action. It demonstrates why the second weather window cannot be treated as an isolated event starting with a clean atmospheric slate. Instead, it inherits a complex set of conditions from the first window, some of which heighten the danger, while others merely complicate the forecast. The interplay of these inherited boundaries, altered ground conditions, and a reloaded thermodynamic profile makes the April 27th to 28th window a uniquely challenging puzzle, in some ways more intricate than the preceding event. While the raw atmospheric ingredients might be slightly less extreme, the mesoscale complexity is significantly greater. This also raises the question of escalation. In a locked weather pattern, later events can sometimes unleash a more powerful atmospheric response. This is because the downstream ridge and upstream trough have had more time to amplify, a process fueled by the feedback from latent heat release. While this outcome is not guaranteed, and current models do not show a definitively stronger signal for the second window, the possibility that it could outperform the first cannot be easily dismissed. The atmosphere is not always winding down. Sometimes it is winding up. Something has been conspicuously absent from the 2026 tornado records for the southeastern United States. In a typical year, by late April, the region colloquially known as Dixie Alley would have already seen several significant severe weather events. This corridor, which stretches across parts of Louisiana, Mississippi, Alabama, Tennessee, and Arkansas, experiences a severe weather season that is distinct from the one on the traditional plains. The unique geography of the Southeast makes it especially vulnerable to certain tornado-producing systems, particularly during the cooler months and early spring when ample moisture from the Gulf of Mexico is available and upper-level dynamics remain potent. Yet, through the middle of April this year, the region has been uncharacteristically quiet. The necessary atmospheric ingredients simply haven't aligned as climatology would predict. The forecast for April 28th, however, signals a dramatic change. As the second shortwave system matures, its warm sector is projected to expand eastward, deep into the Mississippi Valley and beyond. This convergence of returning Gulf moisture, afternoon instability, and the approaching mid-level dynamics of the second cyclone creates a critical window. For the first time this season, the Southeast is poised to enter the severe weather risk zone in a truly meaningful way. The particulars of this Southeastern setup carry all the same uncertainties that have defined this entire 1-2 day period, but they are now layered with additional regional complexities that alter the very nature of the risk. The landscape itself presents a challenge. More extensive forest cover can obscure the visual detection of approaching tornadoes, while also making subsequent damage surveys more difficult. Furthermore, the prevalence of manufactured housing in many rural areas across the region is a known factor that consistently correlates with higher fatality rates during tornado outbreaks. Most critically, this specific episode is forecast to unfold during the overnight hours of April 28th into the 29th. This means the dangerous nighttime risk amplification, a factor we explored for the Thursday event, applies here with equal, if not greater, force. Ultimately, the central question leads back to where this entire narrative began. Even as the Dixie Alley window opens and a new region braces for impact, the fundamental uncertainty remains. Will the atmospheric energy concentrate into a few highly destructive supercells, or will it disperse across many less severe storms? The geography is new, but the profound and unsettling question is exactly the same. Once a forecast extends beyond roughly 7 days, it enters a zone where the most honest answer to many specific questions is simply, we don't know yet. A signal for a potential third severe weather window, projected for the May 3rd to 6th period, has emerged in the extended range guidance of the European model and in a majority of the global ensemble forecast system members. What this means in practical terms is that more model simulations are indicating a pattern favorable for severe weather during that time frame than are showing a calm, quiescent pattern. This is a signal significant enough to communicate, but it must be framed with an honest calibration of our confidence at such a long range. The specific details, such as the precise track of a third cyclone, its central pressure, the resulting storm mode, its exact timing, the placement of the dry line, or the STP values in the highest risk zones, are all variables that have no meaningful forecast skill 10 to 12 days out. What the models are revealing is not a specific event forecast, but rather the structural continuation of the locked atmospheric pattern. This raises a critical question. Why should a low-confidence signal at such an extended range be included in this story at all? The answer lies in the consequences. If this third window does indeed verify, the cumulative context by that point would be unlike anything severe weather responders across the central United States have faced in recent memory. Consider the timeline. By May 3rd, assuming the first 2 windows have produced significant severe weather, emergency managers will have been operating in a state of sustained high alert for 10 consecutive days. The National Weather Service offices covering the Central Plains will have been running extended operational shifts and briefing cycles for over a week. Volunteer fire departments, search and rescue teams, and public health organizations will have already committed precious resources to prior events. Media organizations will have been providing sustained, severe weather coverage for an extended period. The entire emergency response and information ecosystem would be deeply strained. Meanwhile, the public's psychological state becomes a crucial and unpredictable variable. Depending on how the first and second windows unfold, the population will either be in a state of heightened vigilance or, far more dangerously, they may begin to experience warning fatigue. This is a well-documented behavioral phenomenon identified in meteorological risk communication research. When severe weather warnings are issued frequently over a long period, public compliance can decrease. This is especially true if earlier warnings prompted protective actions for events that ultimately proved less severe than the worst-case scenarios described. The danger here is profound. The effectiveness of any warning system is not just in its accuracy, but in the public's willingness to respond. A fatigued public is a vulnerable public, and it's a risk that grows with each passing day in a prolonged, severe weather outbreak. When an alarm sounds repeatedly without consequence, people naturally become accustomed to it. This is a rational response, as the human brain is designed to adjust its assessment of threats based on recent experience. But this habituation, while logical, becomes dangerously maladaptive when a third weather window follows two previous ones. The physics of the atmosphere are entirely indifferent to the social history that came before. It has no memory of having already issued two warnings. This raises a troubling question. Could the pattern be escalating? A third shortwave system, arriving into an environment that has been progressively preconditioned, adds a new layer of concern. If the latent heat feedback mechanism has been active for 10 days, and if multiple cycles of deep convective heating have reinforced the downstream ridge while deepening the upstream trough, then the third event in this sequence could theoretically be the most dynamically intense of all. While this remains speculative, and is not currently the most likely scenario in the models, the physical processes that would allow for it are in play. Acknowledging this possibility is more scientifically honest than dismissing it. The pattern may simply outlast our forecasts, a crucial point to grasp about this third window. It exists on the very edge of reliable prediction, a structural possibility whose final form will be determined by atmospheric processes that will not become clear for several more days. The atmosphere is composing this story in real time, and no computer model available today can reveal its ending. Part 16. 1 tornado versus 100 storms. The same reserve of atmospheric energy can write two entirely different narratives, and the alphabet it uses to choose between them is too small for our forecasts to read. This is the fundamental paradox of the 1-2 day pattern. The energy is undeniable. The dynamics are potent. An STP of 10 is a tangible threat. The conveyor belt of Pacific short waves is a real phenomenon, as is the locked atmospheric pattern. And yet, none of these certainties can resolve the ultimate question. Will this sequence of events generate a single tornado so powerful it will be studied in atmospheric science for a generation? Or will it produce an ordinary series of storms, notable only in hindsight for its compressed timeline? The history of severe weather meteorology offers examples of both outcomes emerging from nearly identical conditions. These precedents are instructive precisely because they show how near identical environmental parameters can lead to radically different results. There are outbreak days in the historical record where an environment with an STP as strong as, or even stronger than, Thursday's was realized. On those days, discrete supercells ignited in the favorable zone, producing long-track, violent tornadoes whose damage paths remain visible from the air decades later. But there are also outbreak days where STP values were just as extreme, yet the outcome was completely different. Storms formed, but their cold pools immediately began interacting destructively. The storm mode quickly transitioned to linear, and the event resulted in widespread wind damage and brief tornadoes, but nothing that qualified as the defining, violent event the setup theoretically supported. What truly distinguishes these two outcomes is not the large-scale environment. Instead, the story is written in the details. The spacing between storms, the interaction of their cold pools, and the precise position of their individual starting points relative to one another. It is a chain of cause and effect events that begins at a scale far too small for deterministic forecasting to resolve. The first storm that ignites sets the stage for the second. The interaction between their cold pools then determines whether a third storm forming between them encounters a favorable or an unfavorable environment. These are like domino processes, but the exact position and velocity of the first domino are not fully known. There is something almost philosophically unsettling about this reality. We have constructed an extraordinary scientific infrastructure dedicated to severe weather prediction. This includes Doppler radar networks that can detect rotation within storms in real time, numerical weather prediction models running at sub-kilometer grid spacing, and ensemble forecast systems that sample uncertainty across thousands of model runs. We deploy dedicated atmospheric research aircraft to fly directly into these environments to gather in situ data. The National Weather Service employs 13,000 people, and the Storm Prediction Center issues outlooks, watches, and mesoscale discussions with a level of sophistication that was unimaginable 30 years ago. Yet for all of that infrastructure, all of that knowledge, and all of that accumulated scientific achievement, we still cannot say for certain whether Thursday will produce one catastrophic tornado or 100 forgettable storms. This is not a failure of science. It is an expression of the fundamental nature of nonlinear, chaotic systems. The atmosphere is a fluid system operating at Reynolds numbers so astronomically high that the deterministic prediction of small-scale features is fundamentally limited. This limitation arises from the propagation of tiny errors in the initial conditions throughout the system. These errors may be small at first, but they double at a characteristic rate. After enough doublings, the specific local details of storm behavior become effectively unpredictable. This is the Lorentz butterfly effect, not as a poetic metaphor, but as a literal physical property of the atmosphere we inhabit. The core issue is one of energy distribution. Will the atmosphere concentrate its power into a few violent events, or will it disperse that energy across many lesser ones? At forecast ranges beyond a day or two, the answer genuinely depends on details in the initial conditions that no observational network can perfectly specify. We can understand the large-scale story, but we cannot know the sentence-level details in advance. This inherent uncertainty is precisely why the forecasting community, when faced with extreme setups, communicates in probabilities rather than certainties and uses conditional language instead of declarative statements. The experienced meteorologist who looks at Thursday's setup and says, "This could be catastrophic, but I cannot promise you it will be," is not being evasive. They are being honest in a way that respects both the science they practice and the public they serve. Part 17. The Cap Problem, the Invisible Gatekeeper. Caught between the vast energy loaded into the atmosphere and the violent storms that might unleash it, there exists a feature with no radar signature, invisible from the ground. Yet this single, unseen variable may ultimately shape the outcome of Thursday's events more than any other. This feature is known as the convective cap, or in meteorological terms, convective inhibition, CIN. It is essentially a layer of relatively warm air positioned just above the surface boundary layer. This warm layer acts like a lid, preventing the buoyant, moisture-rich air below from ascending freely into the upper troposphere. You can think of it as a temperature inversion, a zone where the air, contrary to the norm, actually warms with increasing altitude. This inversion negates the buoyancy that surface air parcels need to rise and blossom into thunderstorms, raising the question of what it will take for this barrier to break. The presence of a cap is not unusual. In fact, it is a common feature across the central United States during the spring and early summer. Its significance lies in its specific thickness and temperature profile, as these properties dictate just how much solar heating is needed to erode it and permit storms to initiate. In a severe weather environment, a moderate cap is paradoxically a key ingredient for the most powerful tornado setups. Such a cap effectively prevents storms from forming too early, allowing thermal and moisture instability to build to extreme levels throughout the afternoon. When this cap finally gives way in the late afternoon or early evening, the resulting storms erupt into an atmosphere primed with a full day's worth of energy. They often fire from a focused trigger, like a dry line, rather than chaotically across a wide area. This is the ideal pathway for the formation of discrete, long-lived supercells. The complication, however, arises when the cap's strength falls to either extreme. If the cap is too weak, it breaks too early and too easily, allowing storms to erupt across a broad region all afternoon. This leads to what meteorologists call an overcooking scenario, where dozens of storm cores are forced to compete for the same pool of atmospheric instability. Their cold pools merge, and the environment quickly shifts into a less dangerous linear formation before the window of peak wind shear is ever reached. In this case, the potential for discrete supercells is lost in its own abundance. Conversely, a cap that is too strong can remain intact through the entire evening peak, suppressing all convection until after the window of maximum instability has closed, or until the dynamic forcing weakens after midnight. Storms that do manage to form in this weakening shear environment can still produce tornadoes, but they are far less likely to sustain the long, destructive life cycles that characterize the most violent and longest tracking events. The forecast for Thursday places the cap's strength somewhere in this delicate middle ground. It appears strong enough to potentially hold through much of the afternoon, yet just weak enough that the combination of late-day heating and approaching dynamic forces from the jet stream and trough could erode it. This break is anticipated to occur near or after sunset across the triple point zone of Oklahoma and Kansas. But the uncertainty in this estimate is significant. The cap's precise strength is determined by the exact temperature and moisture profile of the atmosphere at altitudes between roughly 3,000 and 6,000 feet, and forecast models show meaningful run-to-run variations in these critical layers. Another layer of complexity is the variability of dry line mixing. As the afternoon sun intensely heats the dry, elevated terrain west of the dry line, it creates a deep, well-mixed boundary layer. The eastward mixing of this very dry air can, under certain conditions, erode the cap near the dry line well before the main dynamic forcing arrives. Should this occur, storms would ignite in the early evening before peak wind shear is achieved, placing them in a marginally weaker environment than what would exist just 2 or 3 hours later. Whether these early storms could maintain a discrete structure through the peak window is an open question, depending entirely on their individual behavior and their interaction with the cap in their immediate surroundings. Ultimately, the entire storm mode for Thursday evening hinges on a critical timing window of just 1 to 2 hours. If the dry line initiation occurs 1 or 2 hours earlier than the central forecast, storms will fire into suboptimal wind shear. If it happens 1 to 2 hours later, they will erupt into an environment of post-peak shear, as the atmospheric dynamics are already beginning to wane. The optimal window for historic storms is therefore incredibly narrow, and its exact timing remains uncertain. The difference between these three scenarios, early, optimal, or late initiation, cannot be predicted with any deterministic skill at a 1 to 2 day range. This is the profound power of the invisible gatekeeper. This convective cap, though not dramatic, not visible on radar, and rarely discussed in most weather coverage, controls the final outcome as completely as any of the large-scale features that have dominated this atmospheric story. The cap problem is where it all converges. The 12 days of atmospheric setup, the locked-in pattern, the moisture conveyor belt, the staggering STP value of 10, the triple point, the jet streak, all of that immense complexity, energy, and potential must pass through a bottleneck so narrow that a change of just 2 degrees Fahrenheit in an inversion layer at 8,000 feet could fundamentally redirect the course of events. Given the powerful tornado narrative that has defined this entire event, it would be easy to dismiss the threats of fire, flood, and snow as minor supporting characters. But to do so would be a grave oversight. These are not subplots. They are major events unfolding in parallel, each with devastating potential. The fire weather threat across the southern high plains, for instance, is an emergency in its own right. Across the panhandles of Texas and Oklahoma, official red flag conditions are in effect. This warning is combined with vegetation that has dried with alarming speed following a relatively wet winter, creating the potential for fire spreads that can outpace any ground-based firefighting effort. The fires that have swept through these regions in recent decades have destroyed thousands of homes and buildings, eliminated livestock across vast ranges, and in some cases, moved so quickly that they have trapped vehicles on rural roads. The powerful downslope winds fueling this threat on Thursday will be operating entirely independently of any storm development. They do not need tornadoes to inflict their damage. Meanwhile, far to the north, the flooding across the upper Midwest will compound for days after Thursday's main event. Heavy rainfall from the system's warm sector is forecast to fall upon a drainage system that is already at or near capacity. The resulting floods are a response to their own cumulative loading, a slow-motion disaster unfolding on a different timeline. The rivers do not care whether a tornado occurred in Oklahoma. Their behavior will affect communities across multiple states for days, and perhaps even a week, after the storm system has passed. It is a sobering reminder of how a single weather system can unleash a cascade of distinct hazards, felt hundreds of miles apart, long after the storm's most dramatic moments have faded. In the Dakotas, blizzard conditions threaten to strand livestock, sever transportation routes, and expose communities to the risk of hypothermia. This is the impact of the system's cold sector, delivering a powerful, late-season taste of winter. These hazards, however dangerous, are simply the mechanism through which the atmosphere dissipates its immense energy. Even if the conditions for tornadoes never materialize, if a protective atmospheric cap holds, or if storms cluster inefficiently, the other threats do not simply vanish. The dangers of fire, flood, and snow operate on their own timelines, driven by distinct atmospheric forces, and will unfold regardless of what happens along the dry line on Thursday evening. This is the five-hazard fingerprint of a weather system built like one from January, yet arriving in April, and every one of its threats is profoundly real. Each time an extreme or unusual weather event takes shape, a familiar narrative begins to circulate alongside the official meteorological discussions. It appears on social media platforms within hours of the first computer model simulations, weaving its way through the comment sections of scientific updates. This parallel story suggests that what we are witnessing is not a natural phenomenon, but an engineered one. The claims are varied, but their core message is consistent: that the impending event is the result of weather modification. They speak of chemtrails, seeding storm systems, ionospheric heaters manipulating the jet stream, or government programs secretly manufacturing extreme weather. Some even point to directed energy weapons, steering hurricanes, or cloud seeding operations far beyond any publicly acknowledged scale. Why do these ideas persist with such conviction? The answer seems to lie in a combination of psychology and physics. The atmospheric dynamics that generate a cyclone like the one approaching on Thursday are genuinely intricate, involving the interplay of dozens of variables across vast scales of space and time. From a human perspective, which is finely tuned for pattern recognition, the simultaneous alignment of so many extreme factors can appear less like a coincidence and more like a plan. The atmosphere's behavior can seem too perfectly arranged to be random, its timing too precise to be accidental. Our cognitive processes did not evolve to intuitively grasp systems of this magnitude. Instead, we are wired to detect intention in the actions of others and to see the signature of a plan in the arrangement of our world. When a storm arrives precisely as predicted, intensifies where models suggested, and causes damage that correlates with the landscape, our internal agent detection system defaults to the simplest explanation: someone made this happen. This is where the physics of such claims encounters an insurmountable obstacle: the sheer scale of the energy involved. The total kinetic energy within a single major extratropical cyclone is on the order of 10 to the 20th power joules. It is a figure so vast it can be difficult to visualize, but it is roughly equivalent to the force of several thousand nuclear weapons detonating simultaneously and continuously over a period of many days. That is the energetic reality of just one of these storms. When compared to humanity's entire global energy output, every power plant, every nuclear reactor, every hydroelectric dam, wind farm, and solar panel operating at once, the sum of our efforts amounts to only a tiny fraction of the energy in such a system. In fact, our entire civilization does not generate enough power in a year to match what a mid-latitude cyclone releases in a single day. This staggering energy gap reveals a fundamental truth. There is no available technology, no funded program, and no constructed device capable of generating, steering, or modifying a storm system on this scale. The disparity between atmospheric power and human capability is not a matter of being 10 or 100 times short. It is a difference of many orders of magnitude. To put it in concrete terms, if you were to deploy every aircraft on Earth in coordinated patterns, run every ionospheric heater ever built at maximum output, and scale up every cloud seeding operation by a factor of thousands, the combined energetic input would be thermodynamically invisible. It would be lost against the immense backdrop of what the atmosphere is already doing on its own. You would, in effect, be trying to redirect a river by breathing on it, or attempting to turn a freight train by pushing it with a feather. This comparison is not merely rhetorical. It is a quantitative fact, and the numbers are not close. It is for this reason that the serious atmospheric science community, including researchers who have dedicated their careers to studying deliberate weather modification, regards claims of large-scale engineered weather with the same level of seriousness that physicists reserve for perpetual motion machines. The actual, documented practice of cloud seeding can, under optimal conditions, marginally increase precipitation from clouds that were already primed to produce it. But it cannot create storms. It cannot steer them. It cannot intensify a cyclone, weaken a hurricane, or redirect a jet stream. The entire history of operational weather modification, accumulated over decades of research, has produced interventions so subtle they are only detectable through careful statistical analysis of long-term records. There is simply nothing in that body of work to suggest a hidden, powerful capability waiting to be unveiled. The laws of physics forbid it. The patterns that feel so deliberate are, in fact, the natural result of the very physics we have been exploring. The behavior of Rossby waves, the alignment of the Madden-Julian oscillation, the PNA configuration, and the mechanisms of Lie cyclogenesis. These phenomena feel intentional because they are coherent. They follow physical laws that produce recognizable and repeating structures. In this way, the atmosphere demonstrates its own kind of order, even when that order manifests as catastrophic weather. Coherence is not, by itself, evidence of design. A snowflake is coherent. A galaxy is coherent. The spiral bands of a hurricane are coherent. These beautiful and intricate structures emerge because the equations governing their formation allow for only certain kinds of solutions, and those solutions often appear organized to eyes that are accustomed to seeing organization as the fingerprint of intent. Our planet's atmosphere is an immense engine for generating patterns. It operates continuously, producing these intricate designs, whether we are there to witness them, whether we desire their formation, or whether their emergence serves any human purpose. When the path of a cyclone intersects with our cities, or a storm's timing aligns with a moment of political importance, it can be tempting to search for meaning. But when the geography of the damage appears to follow a recognizable logic, the cause is not some unseen hand arranging these correlations. The truth is that we inhabit a planet where complex weather systems unfold across a landscape we have already transformed, interacting with a civilization we have built and a calendar we have filled with significance. The storm itself remains unaware of our elections, our infrastructure, or our anniversaries. It is simply obeying the physical laws dictated by pressure gradients, temperature differences, and the dynamics of rotation. We are the ones who impose a narrative upon its actions. This brings us to the core of the story, a profound and genuine uncertainty. The impossibility of knowing for certain whether Thursday will bring a single tornado or 100 storms is not the kind of mystery that could be solved by finding a hidden piece of information. Instead, it is the irreducible unpredictability inherent in a chaotic physical system, one that operates on scales far beyond our capacity for perfect prediction. In scientific terms, chaos does not imply pure randomness. It describes how systems governed by deterministic laws can still yield outcomes that are fundamentally unknowable beyond a certain point in time. This occurs because infinitesimally small variations in the initial conditions can amplify into vastly different results. This is the real reason forecasters cannot give you a precise account of Thursday's weather. It is not because they are withholding information or concealing a true cause. The mathematics of the atmosphere itself ensures that all prediction becomes probabilistic past a certain threshold, and no advancement in sensors or computing power can ever completely erase this boundary. It is a limitation that is woven into the very fabric of the physics, a truth that can be more difficult to accept than any conspiracy. The narrative of engineered weather, for all its conspiratorial undertones, offers a peculiar form of comfort. It raises a question about what we find more unsettling. If a hidden agent is causing these events, then it implies that someone could also stop them. The existence of a controller, even a malevolent one, can be psychologically more palatable than the alternative. That alternative is the realization that we live within a planetary scale physical system that can, on occasion, generate outcomes capable of ending thousands of lives for reasons entirely indifferent to our existence. These events are predictable only in terms of probability and remain utterly beyond any human power to prevent or steer away. A storm is not an agent of punishment, nor is it delivering a message. It is simply a consequence of atmospheric physics playing out on a rotating world that is heated unevenly by its distant star. Its arrival on our doorstep is neither personal nor premeditated. It is natural, not engineered. This distinction is critically important, not because engineered weather would necessarily be worse, but because the responses to natural and engineered catastrophes are fundamentally different. One response demands that we prepare, adapt, construct more resilient infrastructure, enhance our forecasting, and ultimately accept that a degree of uncertainty will always remain. The other path sends us on a futile search for imaginary villains, all while the real storm continues its inexorable approach. The cyclone itself has no stake in which path we take. It will arrive on Thursday, all the same. Our choice only dictates whether we will face it prepared or distracted. And true readiness has never been found by looking for an author in a sky that has none. Let us return to the number that began our journey, 986 millibars. This figure represents an extraordinary late April cyclone, one possessing the central pressure typically seen in a deep January system. We are witnessing a storm that exists at the crossroads of abundant seasonal thermodynamics and the dynamic forcing of winter. It is an event that has gathered 5 separate hazard processes across a footprint spanning a continent. It has loaded the atmosphere with STP values that will be recorded in the history books and has locked in a pattern that promises to generate windows of severe weather for 12 consecutive days. Yet, for all its power and complexity, the storm has not yet determined what kind of story it will write. The entire 12-day pattern hangs in a state of atmospheric superposition, with 2 distinct outcomes coexisting within the realm of probability. On one side of this distribution of possibilities lies the concentrated disaster scenario. It begins with a single supercell igniting within the triple point zone over central Kansas or northern Oklahoma at 9:00 p.m. on Thursday evening. It holds its discrete structure because the atmospheric cap remained intact through the afternoon, eroding at the precise moment the peak shear window arrived. As the storm travels northeast through this optimal shear environment, its mesocyclone tightens. A tornado touches down in a rural area, and then it does not dissipate. It remains on the ground, growing in intensity as the supercell draws in increasingly unstable air from the Gulf. For hours, it carves a path northeastward through county after county, widening and strengthening until it becomes the kind of event that forces a rewriting of meteorological records. And as this single tornado unfolds, the second weather window is already loading. And the third is beginning to form at the edge of the forecast models. In this future, the 12-day compression hypothesis is proven correct, and the 2026 severe weather season becomes defined by its first 2 weeks, shaping scientific research for years to come. On the other side of the distribution is the dispersal scenario. This future begins differently, with elevated convection over Nebraska firing early on Thursday afternoon. This activity sends a pool of cold air outflowing southeast into Kansas by early evening. The outflow boundary collides with the dry line, pushing it 50 miles eastward into a region where the atmospheric cap is slightly stronger and surface moisture is somewhat lower. Storms do initiate along this new dry line around 8:00 p.m., but now over eastern Kansas and Oklahoma, and the new cells immediately start to compete with one another. 3 supercells, all within 50 miles, generate their own cold pools that interfere destructively before any single storm can establish a dominant mesocyclone by 9:00 p.m. What could have been a discrete monster has instead merged into a bow echo structure. Significant wind damage occurs from Kansas into Missouri, and while multiple weak tornadoes are confirmed overnight, no single event tracks for more than 5 miles. The total damage is substantial, but ultimately unspectacular. In this version of events, the second window produces a similarly dispersed outcome, and the third never fully materializes, as the pattern lock weakens sooner than the extended models had suggested. Within the realm of what is possible, 2 distinct outcomes currently exist, each held within the same distribution of probability. Neither one is the definitive forecast. Instead, both are equally real possibilities. And it is here that we find the most profound truth about predicting the weather. Our entire scientific endeavor has been constructed around a single goal: to diminish uncertainty, to collapse the sprawling possibilities into a single, confident prediction, and to answer the fundamental question of what will happen with precision. In this pursuit, we have made extraordinary progress. The lead time for forecasting hurricane tracks, for instance, has tripled in the last 50 years. The warning time for tornadoes has grown from virtually 0 in the 1950s to an average of 13 minutes today. With every new generation of numerical models, our ability to forecast precipitation has improved dramatically. The science is, by any genuine measure, advancing. Yet, here we are, 48 hours before one of the most dynamically extreme weather setups for late April in the modern record, and the most essential question remains unanswerable. Will this energy manifest as a concentrated catastrophe, or will it scatter into a series of lesser events? This is not due to a failure of science or a lack of data. It is because the very physics of the situation, non-linear, chaotic, and scale-dependent, places this specific detail beyond the grasp of deterministic prediction at this range. The first domino is poised, but the path it will carve remains a mystery. The array of known factors is both impressive and unsettling. The 1-2 day window of potential activity is real. The locked-in atmospheric pattern is real. A significant tornado parameter, or STP, of DES is real. The convergence of 5 simultaneous hazard processes is real. So too are the atmospheric conveyor belt, the feedback from latent heat, the stalled Rossby wave, and the alignment with the Madden-Julian oscillation. Every one of these components is a verifiable fact, and together they tell a clear story. The atmosphere has assembled something truly extraordinary over the central United States. But what this powerful assembly has not yet told us, what it cannot yet tell us, is how this story ends. Will this extraordinary energy be converted into extraordinary history, or will it simply disperse into the background noise of the season, a loaded chamber that was never fired? The potential is immense, but its final expression is a chapter that has yet to be written. There is a strange beauty in this uncertainty, a sense that the atmosphere itself has not yet chosen its path. The specific arrangement of air molecules in the boundary layer over central Oklahoma at 8:47 p.m. on Thursday is an event that still resides in the future, unwritten and undecided. This state of being is what quantum mechanics might call a superposition of possibilities, and what meteorology describes as a probability distribution. The cat is, for now, both alive and dead. The tornado is both present and absent. A season-defining catastrophe is at once both certain and impossible. When Thursday night finally arrives and the atmosphere makes its irreversible choice, that decision will be the culmination of countless tiny variables. It will be made by a pressure gradient at 986 millibars, by a jet streak moving at 130 knots, or by an atmospheric cap that either held firm or broke at precisely the wrong or right moment. The outcome could hinge on a cold pool boundary from Nebraska that travels 50 miles in a critical direction, or the specific dew point value at a single surface station that either nurtures or starves the one supercell that becomes the story. The pattern is certain, but the narrative it creates is not. This profound uncertainty keeps atmospheric scientists, storm chasers, and forecasters awake at night. It is not a feeling of dread, but rather a unique state of alertness that comes from watching something enormous and irreducible approach. The next 12 days will not unfold as a single story, but as a series of decisions the atmosphere is about to make, one after another. Each of these moments will be shaped by the ones that came before it, and each carries the dual possibility of a concentrated disaster or a more dispersed consequence. Every step of the way, the environment bears the objective, measurable fingerprint of an atmosphere primed for violence. We see it in Window 1, Window 2, and Window 3, each a new question, and each with the same elusive answer, hidden somewhere in the chaotic arithmetic of a fluid system that has been running its calculations since before humans had words for its creations. We have words for it now, and we have numbers. We see the 986 millibars, the STP of 10, the 130 knot jet stream, the 4 8 to 7 2-hour recurrence. We have 3 windows of opportunity over 12 days. We possess almost everything except the one thing that matters most, the ending. The atmosphere, indifferent to our forecasting frameworks, our ensemble models, and our carefully worded discussions, is writing that ending right now. It is being composed one parcel of air at a time, in a language that operates below the resolution of every tool we have built to read it. The pattern is set in stone, but the story it writes remains fluid and unpredictable. And somewhere in that gap, between the certainty of the environment and the uncertainty of the outcome, lies the truth of our fascination. It is found between the 986 millibar cyclone that should not exist in April and the tornado that may or may not ever touch down. It is in the space between the scientific precision of the STP index and the chaotic, irreducible nature of a convective trigger. Somewhere in all of that lives the actual, honest, unvarnished answer to why we watch the sky. We are captivated not because we know what it will do, but precisely because we do not. We are witnesses to a story being written in real time, a grand, unfolding narrative whose final page has yet to be revealed.